Video, we'll do some additional practice final exam problems taken from the practice exams on the course website. And these problems will be taken from practice final number 2. So that means you go to the Pages tab and then the final exam page. And this is practice final number 2, and this is problem number 9. It asks us to find the first 5 non-zero terms of the Maclaurin series for f of x equals 1 minus x to the minus 2. Then we'll have some Maclaurin series. We want to figure out the radius of convergence of that power series. So there's 2 good ways to do this, and I'll show you both of them. But the first one, we're going to notice that the function we're asked about is really, really close to a function we know well. 1 over 1 minus x is the very first power series expansion, like representation of a function as a power series that we looked at. That is 1 minus x to the minus 1. And we can write this as a power series. This is the geometric series, sum x to the n. And this is valid for absolute value of x less than 1, which means r equals 1. Okay, so now the thing to do is notice that we get from the function we have here to the function we want by taking a derivative. What is the derivative of 1 minus x to the minus 1? Well, you apply the power rule. You get a minus 1 that comes down, and you get 1 minus x to the minus 2, and then an extra minus 1 from inside from the chain rule. So let me just write this more carefully. d dx, 1 minus x to the minus 1 equals minus 1 minus x to the minus 2 times minus 1, which is 1 minus x to the minus 2, which is exactly the function that we want to find a power series representation of. Okay, so if we differentiate both sides, the power series representation here is going to be the power series we get by differentiating x to the n 1 term at a time. So we get n times x to the n minus 1, where, okay, when n equals 0, this is just 1, so we should get 0. But 0 times x to the negative 1 is the same thing as 0. So this is okay. But if you like, maybe it's better to start this series at 1. Either way of writing it is okay. And then a really standard thing for power series is to start at your variable being equal to 0 instead of 1. So if we let m equal n minus 1, so okay, that means n equals m plus 1, then this series is the same as the sum from now m equals 0 to infinity of m plus 1 times x to the m. And the key thing here is that when you differentiate a power series 1 term at a time, the radius of convergence does not change. Okay, but we're not actually asked for the Maclaurin series here. We're asked for the first 5 non-zero terms. We have the whole thing. But this is just saying, like, put in m equals 0, m equals 1, m equals 2, m equals 4, and see what you get. And what we get is 1 times x to the 0, which is 1, plus 2 times x, plus 3 times x squared, plus 4 times x cubed, plus 5 times x to the 4th, plus, 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 plus. Okay, so this is our first solution to this problem. I'll start the second solution, but at some point I'll have to pause and erase for space. Okay, so suppose you don't see this connection between 1 over 1 minus x and this 1 minus x to the minus 2. Then how do you write down the Maclaurin series of any function? Well, you know, our goal is to write this as a sum from n equals 0 to infinity of Cn times x to the n. This is a power series centered at 0. Maclaurin series is Taylor's series centered at 0. And we know that Cn has to be equal to take the nth derivative of f evaluated 0 and divide by n factorial. So what's the idea? Well, it's the same as it is for many of these Maclaurin-Taylor series problems, is we'll compute the first few derivatives and find a pattern. So let me just say for short, find a pattern with fn 0. So this is the part that we have to do. So I'm going to pause and erase, and I'll compute the first few derivatives, and we'll see if we can use that to write down the whole Maclaurin series. Our goal is to write down the Maclaurin series of this function. So we have to find a pattern for these, take the nth derivative of f and evaluate at 0. So I just wrote out the first term as the 0th derivative is just 1 minus x squared. So what happens when we take a derivative? A minus 2 comes down from the power rule, and we get an extra minus 1 from taking the derivative of the inside with respect to x. So we get minus 2 times minus 1, the minuses cancel, and we get 2 factorial times 1 minus x to the minus 3. The exponent comes down by 1. So let's take the derivative again, and let's see if we can start to notice a pattern. So the minus 3 comes down, we get minus 3 times 2 factorial, and we pick up an extra minus 1 from taking the derivative of the inside in the chain rule. So we get minus 3 times minus 1 times 2 factorial times 1 minus x to the minus 4. The minuses cancel, we just get 3 factorial times 1 minus x to the minus 4. If we take one more derivative, the minus 4 comes down, we get an extra minus 1 from the inside, so we get minus 4, minus 1, 3 factorial. The minuses cancel, and this is just 4 factorial times 1 minus x to the minus 5. Let me write it here. 4 factorial, 1 minus x to the minus 5. And if you just continue in this way, after n derivatives, every time you get a new number coming down that's 1 more than the factorial you had before, and a negative, and then you get another negative from the inside. So what you get is just n plus 1 factorial times 1 minus x to the minus n plus 2. Why n plus 2? Because at 0, we started with minus 2. Okay, but that's not exactly what we need. We need to see what happens when you evaluate at 0. So you put in 1 minus 0 to the minus n plus 2, and that's just 1 to the minus some number, and that's just 1. So what you get is n plus 1 factorial. So that means Cn equals n plus 1 factorial over n factorial, which is n plus 1. So the Maclaurin series for this function, 1 minus x to the minus 2, is just a sum from n equals 0 to infinity of n plus 1 times x to the n. And this is the same power series that we got before. So one difference here is if you don't get this power series by noticing that you can start with the geometric series and take a derivative and use the fact that when you take a derivative, the radius of convergence doesn't change, you have to find what is the radius of convergence. But if you just use the ratio test, what you end up doing is taking the limit as n goes to infinity of, if this is an, then what you get is n plus 2 over n plus 1 is just 1. So what we get here is that the radius of convergence is r equals 1, but you have to do something to check the radius of convergence. So again, starting from here, remember what you're asked for are the first 5 non-zero terms of the Maclaurin series, but I find that the easiest thing to do is compute the whole Maclaurin series and then just write down what the first 5 terms are. For our next problem, let's do number 13 from practice final number 3. So that is, go to the Pages tab in the final exam page. This is practice final number 3. And this is not an exam that I wrote. This, again, just like the previous one, is a practice final exam from when Math 2B had a common final. But this is the kind of problem that you might expect to see. So we want to find a power series representation for 2 over 3 minus x and we want to determine the interval of convergence. And the idea is that this is kind of close to 1 over 1 minus x, which is the power series we know best, the geometric series, where this converges exactly in the interval I from -1 to 1. So it's a power series centered at 0, radius of convergence 1. So we would like to take 2 over 3 minus x and write it as something times 1 over 1 minus something. Because then we could use the geometric series power series to write down this one. So we can factor out a 2 for sure. And we can think of this as 2 times 1 over 3 minus x. But this 3 minus x is not ideal. It would be better if it was a 1. So if we factor a 3 out of the whole denominator, we get a 1/3 and then 1 over 1 minus x over 3. So this is 2/3 times 1 over 1 minus x over 3. And we know a power series representation for 1 over 1 minus x over 3 is just take the one that we have for the geometric series, and everywhere we see an x, let's put in x over 3. So this is a sum from n equals 0 to infinity of 1 over 3 to the n times x to the n. And when does this power series converge? Well, you could do the whole thing with the ratio test, and you would see the same answer that you get from just noting that 1 over 1 minus x converges exactly when x is between -1 and 1, when absolute value of x is less than 1. So any power series of the type 1 over 1 minus something is going to converge when that something is less than 1 in absolute value. Absolute value of x over 3 is less than 1, which is the same as saying absolute value of x is less than 3. So that is for x in the interval from -3 to 3. Okay, but remember, last thing. This is not quite the power series we were asked for. We're asked for 2 over 3 minus x. So what we get is 2 over 3 minus x equals a sum, n equals 0, infinity, 2/3 times 1 over 3 to the n, x to the n. And if you like, you can put the 3's together. So you can write this as sum, n equals 0, infinity, 2 times 2 over 3 to the n plus 1 times x to the n. And when does this converge? The interval of convergence is exactly the interval from -3 to 3. So this is a very standard type of example that you might expect to see on the final exam. For this final example, let's do a problem from practice final 4, number 9. So this is not an exam I wrote either. This is a practice final from another instructor, but one whose style I very much like, so you should expect to see a problem like this on the exam. Find the interval of convergence of the power series, sum from n equals 2 to infinity of x minus 3 to the n. Well, how do we do these find the interval of convergence problems? Is the first step is always the ratio test. So here's an. And our goal is to say something about the limit of the absolute value of an plus 1 over an. So what does that look like? We have big absolute values, x minus 3, n plus 1 over 2 to the n plus 1, square root n plus 1, divided by x minus 3 to the n over 2 to the n, square root of n, parentheses, parentheses, which 2 to the n plus 1, square root of n plus 1, 2 to the n, square root of n, that's all positive. So the only role that the absolute values play have to do with the x minus 3 powers, which may be positive and may be negative. Okay, there's a lot of cancellation here. And then what we get is 2 to the n over 2 to the n plus 1, a lot of cancellation here. And then we get a square root of n over square root of n plus 1. You can write this way more nicely. This is absolute value of x minus 3 times 1/2 times square root of n over square root of n plus 1. This is very similar to a problem that we did earlier. If we take L to be the limit as n goes to infinity of this expression, we see that square root of n over square root of n plus 1 goes to 1. It's not hard to check. So this is just absolute value of x minus 3 over 2. So the ratio test says that S converges if absolute value of x minus 3 over 2 is less than 1. And it diverges if this absolute value is bigger than 1. But what does this absolute value being less than 1 mean? Absolute value of x minus 3 is less than 2. So this means x is in between 2 steps away from 3 in either direction, 1 to 5. 1 is the value that gives you negative 2 on the left side. 5 is the value that gives you positive 2. So that's not enough to determine the interval of convergence. We know that if x is completely outside this interval, L is going to be bigger than 1, and the series will diverge, but we have to check the endpoints. So what do I mean check the endpoints? These two values where L is equal to 1, that is, we'll plug in x equals 1 and see what series we get, and plug in x equals 5 and see what series we get, to see whether we should include these endpoints when we describe the interval of convergence. So I'll pause and erase, and then we'll finish up this problem. Let's check the endpoints. So when x equals 1, S is equal to a sum from n equals 2 to infinity of 1 minus 3 to the n over 2 to the n square root of n, which is a sum n equals 2 infinity minus 2 to the n over 2 to the n square root of n. Minus 2 to the n is 2 to the n times minus 1 to the n. So the 2 to the n's cancel, and we get a sum from n equals 2 to infinity of minus 1 to the n divided by square root of n. So this series is alternating. Terms go plus minus, plus minus, plus minus, plus minus. And the bn terms, the things not being multiplied by the minus 1 to the n, are decreasing and going to 0. So this series converges by the alternating series test. So we should include x equals 1 in our interval of convergence. What about when x equals 5? Well, we get s equals sum n equals 2 to infinity, 5 minus 3 to the n, that is 2 to the n, over 2 to the n times square root of n. So we get left with 1 over square root of n. And this, we know, diverges because this is a p-series with p equals 1/2. So what we've seen is that S converges if and only if x is in the interval of convergence from 1 to 5, including 1, but not including 5. So the interval of convergence includes the bottom endpoint, but not the top endpoint. So what happens here? The first step is always the ratio test. You have to do some algebraic cancellation to get the limit into a form where you can take it. You see what it means for that limit L to be less than 1. And then you have to check the endpoint separately. So you have to do something else to see some other series test. See what series you get when you plug in the lower endpoint and when you plug in the top endpoint. And for each of those two series, you have to do some series test to see if they converge. So this is a very standard find the interval of convergence of the power series type problem.